Good day everyone. We are Group 5 and we'll be presenting the phosphorus industry. To start off, I would like to first introduce my team members that made this PowerPoint and presentation possible. For the overview and background was handled by Malinis Patrick, production processes by Paclibar Arnil, raw materials and products by Razon Gerald, and finally, yours and truly, the PowerPoint creator and your presenter for tonight, Dayap. The objectives are to achieve the following in this presentation: to discuss the background and overview of phosphorus, the colors of phosphorus, the uses of phosphorus, the phosphorus industry in the Philippines, raw materials for white phosphorus production, raw materials for red phosphorus production, equipments used in the production, governing chemical reactions, process diagram for white phosphorus, process diagram for red phosphorus, and the references in the end. Background and overview. Elemental phosphorus was discovered around 1669 by the German alchemist Henning Brandt. The name phosphorus is actually derived from the Greek word phos meaning light and phoros meaning bearer, the same name given by ancient Greek and Roman astronomers to the planet Venus when it appeared in the sky in the morning star. It is a chemical element with the symbol P and atomic number 15. Its elemental phosphorus exists in two major forms, white and red. It is one of the most in-demand phosphorus in the industry. But because of its highly reactive component, phosphorus is never found as a free element of Earth and thus needs to be produced through industrial means. From the perspective of applications and chemical literature, the most important form of elemental phosphorus is white phosphorus, often abbreviated as WP. Like the rainbow in the sky, phosphorus can come in many shapes and sizes, but most importantly, in different colors. White phosphorus, when exposed to oxygen, it glows in the dark with a very faint tinge of green and blue, very flammable and pyrophoric, meaning self-igniting, upon contact with air. Owing to its pyrophoricity, white phosphorus is used as an additive in napalm, and it's insoluble in water, but soluble in carbon disulfide, and mostly used in explosives. Red phosphorus may be formed by heating white phosphorus to 250 degrees Celsius or by exposing white phosphorus to sunlight. Phosphorus after this treatment is amorphous. Upon further heating, this material crystallizes. In the sense, red phosphorus is not an allotrope but rather an intermediate phase between the white and violet phosphorus. The violet phosphorus is a form of phosphorus that can be produced by day-long annealing of red phosphorus above 550 degrees Celsius. In 1865, Hittorf discovered that when phosphorus was recrystallized from molten lead, a red-purple form is obtained. Therefore, this form is sometimes known as Hittorf's phosphorus, or violet or alpha metallic phosphorus. Lastly, black phosphorus. It is the least reactive allotrope and the thermodynamically stable form below 550 degrees Celsius. It is also known as a beta metallic phosphorus and has a structure somewhat resembling that of graphite. So as you can see the pattern, it starts from white phosphorus, and as you add more heat and more time, it changes into different colors where each color represents different uses of that certain phosphorus. Surprisingly, phosphorus has many uses in the industry today. One of which, phosphorus is used as explosives. There are various allotropic forms of phosphorus as discussed earlier, but only two forms have commercial significance, the white and the red phosphorus. And white phosphorus is the most commercially important, accounting for 99% of the demand worldwide. In general, white phosphorus is used in flares and incendiary devices, whereas red phosphorus is in the material stuck on the side of matchboxes used to strike safety matches against to light them. Phosphorus can also be used as fertilizers, for they are very important in a plant's life cycle, for it converts nutrients into its building blocks of growth. And is also one of the main three nutrients found in fertilizers today. Hence, one of their ratings for fertilizers is the NPK rating, or the nitrogen, phosphorus, potassium rating. It can also serve as chemical intermediates such as phosphoric acid used in soft drinks to create phosphate compounds, triple superphosphate for fertilizers, trisodium phosphate for cleaning agent and water softeners, calcium phosphate for baking powder production, and the other phosphate types or phosphorus compounds glow in the dark or emit light in response to absorbing radiation, and are therefore also used in fluorescent light bulbs and television sets. The other notable uses for phosphorus are ingredients for the production of steel, ingredients also for the production of detergent. However, detergents are beginning to be phased out in some countries. This is because phosphorus can also lead to high phosphate levels in natural water because of the amount of phosphorus in detergents. Therefore, phosphorus is a very tricky chemical to use. That's why there are many chemical protocols involved before phosphorus can be used in mass production. Also, phosphorus can also be produced in using special glasses and fine chinaware. Today, there are numerous and notable companies that paved the way for the phosphorus industry in the Philippines. One of these companies is named the Philippine Phosphate Fertilizer Corporation, or PhilPhos for short. They manufacture and distributes agricultural fertilizer. This company produces phosphatic fertilizer and sells its products throughout wholesalers and retailers throughout the Philippines, Vietnam, Thailand, and Indonesia. Their products include ammonium sulfate, diammonium sulfate, NPK fertilizer, phosphoric acid, and sulfuric acid. Another well-known company that produces phosphorus is the Atlas Fertilizer Corporation. The Atlas Fertilizer Corporation, or AFC, incorporated on October 10, 1957, is the oldest operating and the first fertilizer company in the Philippines to achieve full-scale manufacturing of a complete line of mixed fertilizer grades, alternatively known as compound inorganic fertilizer and more famously called by our farmers as the NP, NPK, NK fertilizers. Here are their sample fertilizers, one of which is the Atlas Perfect Grow 14-14-14 and the Atlas Diammonium Phosphate 18-46-0, where the second product contains 80% nitrogen and 46% phosphorus. And this company actually produces different types of ratios and balances depending on the ingredients per fertilizer to assure and to assist the different farmers pertaining on their different farming needs and for their different crops. The third company, also well known in the Philippines, is the Chemres Technologies. Chemres Inc. Chemres Inc., born in 2006, was acquired by fellow DNL subsidiary Coro Coat Incorporated to form what is known as the Chemres Technology Incorporated, which operates the Philippines' first continuous process biodiesel plant. The Chemres Technologies products are not limited to phosphate production only, where their products include crop enhancers, petroleum and oil field chemicals, personal care and hygiene products, home care, and packaging products. An example would be their new 3-in-1 organic product acting as insecticidal oil, pesticide enhancer, and sticker oil, also known as the Crop Guard. And this is their sample products, one of which is the Crop Guard as mentioned earlier, and the foliar fertilizer, the complete plant food that also has different ratios pertaining to the farmers' different farming needs or their specific crops. Already knowing that the white and red phosphorus are the most produced and commercially in-demand phosphorus chemicals that are in the industry today, and as such, we will only focus on the production, raw materials, and equipment used and needed for their production, which is the white and red phosphorus specifically. To start, let us know the raw materials for white phosphorus production. One of which is the fluorapatite or apatite. Apatite is one of the most common raw materials which acts as a primary source of elemental phosphorus, P4. The process requires the reduction of apatite to produce the said product, phosphorus. Another apatite type is a fluoroapatite. Fluoroapatite is a specific part of the apatite group which is considered as a phosphate material. A phosphate material is a group of minerals which has naturally occurring inorganic salts of phosphoric acid. The second material for white phosphorus production is coke, not the beverage, but the stone. Solid residue containing high contents of carbon, coke is made from heating coal at high temperatures with absence of air. The solid residue produced from low ash, low sulfur bituminous coal baked at high temperatures, making fixed carbon and residual ash fused together. Another ingredient is silica, which can be found on gravel or quartz. Also known as silicon dioxide, SiO2, the Earth's crust is comprised of by a huge percentage of silica by around 59%. The silica acts as a flux, converting the calcium oxide form into a low melting slag during the production process. This slag also incorporates most of the impurities brought into the production with the ingredients with the exception of iron and part of the fluoride. Now for the raw materials used for red phosphorus production, which is white phosphorus. Because how does red phosphorus occur? It's only due to the heating of white phosphorus. Red phosphorus is primarily formed by heating white phosphorus to temperatures of around 250 degrees Celsius, causing the material to crystallize. And another ingredient for red phosphorus production is water. Some processes include a condensing system with water which uses steam to make reduced phosphorus loss from the production process. Long story short, in order to get the other forms or colors of phosphorus, such as red, black, violet, you first need to produce white phosphorus. And since the industry only wants white or red phosphorus, then in order to get red phosphorus, you need to produce white phosphorus. Since, in long story short again, to get red phosphorus is just a heating and cleansing of white phosphorus. And white phosphorus needs to follow certain steps from raw materials in order for that to be produced. In order to produce the white and red phosphorus, certain types of equipment must be present. The first of which is the electrothermal reactor. This device allows the reaction from the raw materials to take place to produce the said phosphorus. And this is where the raw materials are being burned, and the output stream of the electrothermal reactor are carbon monoxide, phosphorus vapor, ferrophosphorus, and the slag. After passing to the electrothermal reactor, it went now to a filter. The dust from the electrothermal reactor is then filtered in order to clear the phosphorus products from the impurities. After filtration, it then goes into a condenser, where the filtered carbon monoxide and the phosphorus vapor is condensed by using water at specific temperatures in order to produce the solid and liquid white phosphorus. But for red phosphorus, it uses the same machines, but an additional machine is also added in place. And that additional machine for red phosphorus production is the vaporizer, because the reacted molten white phosphorus was vaporized in order to form the red phosphorus vapor and carbon monoxide vapor. So in short, in general, in order to create white phosphorus, you need the electrothermal reactor, the condenser, and the filter. But for the red phosphorus, you need all three machines and an additional machine, which is the vaporizer. For phosphorus production, it's not just as simple as having the raw materials, which is coke, apatite, gravel, silicon, and etc. Put it into a reactor and boom, you have your phosphorus. It's not that simple, because there is a governing chemical reaction that oversees this process itself. And this is the governing chemical reaction. To start off, one of the first governing chemical reactions is the interaction between apatite and carbon monoxide. So 1 atom of apatite mixed with 5 atoms of carbon monoxide at a very, very high temperature, 14,000 degrees Celsius, will yield 3 atoms of calcium oxide, 5 atoms of carbon dioxide, and 2 atoms of phosphorus. Then a side reaction will also occur, which is 5 atoms of carbon dioxide mixed with 5 atoms of carbon will yield 10 atoms of carbon monoxide. Combining these two equations together, just using the Hess law properties, you will get a governing chemical reaction where apatite plus 5 atoms of carbon will yield 3 atoms of calcium oxide plus 5 atoms of carbon monoxide plus 2 atoms of phosphorus. Phosphorus is mainly produced through the electrothermal reduction of apatite with coke in the presence of gravel. So this means that this apatite component already has the presence of coke and gravel in them. The carbon monoxide is regenerated from carbon dioxide and coke. The silicon acts as a flux, converting the calcium oxide into a low melting slag. And as such, the slag also has its respective chemical reaction. The balanced chemical formula for the slag is calcium oxide plus silicon dioxide will yield calcium silicate. In order to produce the white phosphorus production, we already know the equipment needed, the raw materials, and the governing chemical reactions. Now we need to know is the procedure or the steps itself on how to produce white phosphorus. So this is the process flow diagram for the production of white phosphorus. It may look scary at first, but it's just telling a story from the raw materials to the desired white phosphorus. And let's start off the story by the raw materials, coke, gravel, and apatite pellets, which are all fed and mixed into one feed stream towards the electrothermal reactor. One of the outputs of the electrothermal reactor, or there are three outputs in the electrothermal reactor. The first output is the ferrophosphorus, which is set aside for it is not really needed for this type of process diagram. Another output is the slag, or the slag stream, and this slag will have a use within the process diagram later on. But the main stream that we want to know, or we want to have, is the stream mixture, which has the mixture of phosphorus and carbon monoxide. This stream is therefore fed into an electrostatic filter, where its output, one of its output, is the filter dust. And this filter dust is fed into a granulator, where apatite are also fed into the granulator itself. One of the outputs of the electrostatic filter, going back, is the same stream of phosphorus and carbon monoxide, and this is also fed into a condensation tower, where in order for the condensation tower to work, it needs water as its another feed stream. This is condensation tower 1. One of its outputs is one of our needed, the white phosphorus in liquid form. And the other is the condensation tower's output is another stream, which is the phosphorus carbon monoxide stream, and this is also fed to another condensation tower named condensation tower 2. And one of the outputs of the condensation tower 2 is one of our needed white phosphorus, but in solid form. And in order to make the process diagram more efficient and in a cycle to have a greater yield of white phosphorus, one of the outputs of the condensation tower 2 is just the carbon monoxide alone, hence the carbon monoxide stream. This carbon monoxide stream is therefore sent into a dryer. Also, the granulated stream is also sent to a dryer. And as such, one of its outputs is the main recycling stream, where this recycled stream is also mixed with the slag stream from the electrothermal reactor. Thus, 3 streams into one recycled stream goes back to one of the raw materials, which is the apatite pellets. Therefore, the process diagram has maximized its efficiency, and it is in a cycle that will yield the maximum possible white phosphorus in liquid and solid form. And in order to make this very vibrant and also very easy to understand, this is the graphical representation or a picture representation of the process diagram itself. Instead of having labels or words, we'll just use pictures so that we'll get even greater information at first glance. And some important notes: at condensation tower 1, water at condensation tower 1 must be at 50 to 60 degrees Celsius to produce liquid phosphorus. And at condensation tower number 2, water must be at 10 to 25 degrees Celsius to produce, this is a typo, this is supposed to be solid white phosphorus. Solid white phosphorus at water must be 10 to 25 degrees Celsius at condensation number 2. And the ferrophosphorus is considered one of the byproducts, which are covered in black, labeled earlier, is considered as a byproduct, and it's not really used, as I said, for the process diagram. However, it is used in metallurgy. So this byproduct can be recycled or can be reused into another industry, which is in the metal or metallurgy industry, so that every byproduct produced in this process diagram is used to its maximum potential. Remember what I discussed earlier, that the red phosphorus is just merely a product of a white phosphorus with greater heat and another water stream? Well, the process diagram at first glance is just like that. However, it's much more than that. So this is at first glance the process diagram for converting the white phosphorus to the red phosphorus. It's very scary, I know. But again, it's just telling a story from how we get the raw material, which in this case is not coke, apatite, or silica, but white phosphorus, and converting it into red phosphorus using certain procedures or certain steps. Let's start with the first step. When the white phosphorus is then mixed with water into a feed drum. This feed drum stream is therefore fed into a reactor, which is also cooling water is also fed into the reactor itself. Then the output stream of the reactor goes into the vaporizer, where one of the outputs of the vaporizer is the mixture of carbon monoxide vapor and white phosphorus vapor. And another stream, the other stream of the first vaporizer is sent into another vaporizer where heated carbon monoxide gas is also fed in the second vaporizer. Then the output of the second vaporizer is then fed into a wetting tank where water is also fed into the wetting tank. The output of the wetting tank is then settled into a settling pan where one of the outputs is a drained water. So as the molecules settle in the settling pan, the water is drained, and what's left in the settling pan after the drained water is our needed red phosphorus output. So this is the overview on how to convert white phosphorus to red phosphorus. However, this is not efficient. So we need to make the cycle or the process diagram more efficient and more eco-friendly, economical friendly. So remember that one of the outputs of the vaporizer is a mixture of a white phosphorus vapor and a carbon monoxide vapor. Well, this stream is therefore fed into a spray condenser where one of its output is a carbon monoxide vapor which is exhausted from the spray condenser, and another output, the other slurry, is then fed into a settling basin. Then one of the outputs of the settling basin is the white phosphorus solid, where white phosphorus is now in solid form. Then it is then recycled back into the raw white phosphorus feed stream towards the feed drum. So this is where the recycle comes into place. And another output of the settling basin is when water overflows in the basin itself. This overflowing water is fed into a water heater, where another feed stream of the water heater is a mixture of water in liquid form and water in vapor form, or in steam. Which in the water heater, water is at this point is already heated. The stream that contains water in liquid and water in vapor form. One of the outputs of the water heater is a drained water where it is discarded, and another output is the slurry, which goes back to the spray condenser. Thus, another cycle is present in the process diagram. So there are two cycles, one of which is the cycle from the vaporizer back to the white phosphorus, and a second cycle is within the spray condenser and the water heater to the settling basin. And in order to understand this, well, at first glance, again, this is the graphical diagram or diagram with pictures that can help you understand at first glance the information and what does the equipment and the process look like, so that to avoid any misconceptions. And here are some important notes for the process diagram. Liquid white phosphorus is continuously fed to the reactor, producing a uniform mixture of red and white phosphorus. In the first vaporizer, carbon monoxide and white phosphorus vapor was extracted from the slurry, then condensed using water, producing white phosphorus, and the carbon monoxide is released as exhaust. The produced white phosphorus is recycled back to the feed drum, as you can see at the recycling stream earlier. The carbon monoxide and red phosphorus vapors was subjected to a wetting tank, producing a slurry containing water and red phosphorus, and therefore solid red phosphorus is produced from solid white phosphorus. And that is all for the presentation. Here are the references, and the group used numerous references in order to make this PowerPoint possible. And again, my name is Ron Dayap, representative of the Phosphorus Group 5, and I would like to thank you all for listening to our presentation. Thank you and good day.